Thomas, for being here today with us.
Okay. Well, first of all, thank you very much for inviting me to this workshop. I must admit that I arrived this morning and already the first two talks were really, really nice and really inspiring. So I hope mine will be at the same level of quality. Well, as Christina just said, I will report on what's the status right now regarding the discovery of this. Is it working? Well, not sure. Okay, never mind. Of the diffuse supernova neutrino background. And well, my talk will be ordered the following way. So first, I will give a few words about this, supernova neutrinos and this DSNB. And then I will present you the main detection channel, gives you the current status of the different DSNB searches, and a few words about the next generation experiments. And then the last part of my talk, which will be probably the dominant part, will concern the latest results that we have obtained with Super Kamiokande, with its gadolinium doping, which were presented at Neutrino 2024 conference. Well, concerning supernova, we already discussed about that this morning, but you all know that core collapse supernova are among the most cataclysmic events that occur in our universe, and that they are really key ingredients of the dynamics of the cosmos. Although they have been studied, the explosion mechanism is still not fully understood. And the reason for that is because we would need to have insight of what happens inside the core of the collapsing star. And for that, neutrinos are a very good probe in the sense that we have a lot of them emitted during a supernova explosion. Roughly 99% of the gravitational binding energy is emitted in the form of neutrinos, and that they carry information about the core. Well, so far, sadly, only one supernova has been detected in its neutrino signal, and that was the very famous 1987A, where you have the events here detected in Camlin 2 experiment in IMB. And all currently running experiments are ready to observe such an event. Typically, 1987A was in the Magellanic Cloud, but if we imagine an explosion in the center of our galaxy, that would be roughly 8,000 neutrinos in Super Kamiokande. So that would be really interesting. However, the rate of supernova is fairly rare in our galaxy, few events per century, but supernova are not rare within the visible universe, where we expect typically, one supernova per second. And this triggers, in fact, the search for, yes, thank you very much, for the diffuse supernova neutrino background. Well, the reason for that is that if we consider neutrino are a stable particle or long-lived enough, we are living in a universe which suffused all the neutrinos of all flavors which have been emitted by all the past supernovas. Of course, they have been redshifted, but we can technically observe this flux if it is high enough. And well, it depends on several ingredients. It depends, of course, on the neutrino emission process from the collapsing star. But you see that through the observation of the DSNB, you also have information on the rate of supernova, which is directly linked to the star formation rate. And you also have information about the universe expansion history. And typically, the energy spectrum that you expect does depend on the redshift because the energies would have been redshifted. Now, this, I think I should be here. So these are the prediction from several models, and you can see that currently there is at least a factor 10 differences between the different models. And the observation of the DSNB would shed the light on which model predicts this DSNB correctly. And the key ingredients in the models don't have the same impact on the DSNB. The normalization of the spectrum is mostly related with the cosmic star formation rate, whereas the shape of the spectrum does depend on many parameters. It depends, for example, on the fraction of failed supernovae, I mean black hole forming supernovae. It's related to the effective core temperature, which relates with the neutrino energy. And subdominantly, but still, you have effects of the expansion of the universe, of the neutrino oscillation, and especially the propagation of neutrinos in ultra-dense matter. And you can also probe effects like neutrino decay or other non-standard interaction. So observing the DSNB would allow us to access to a very rich physics program, of course, depending on the precision on the spectrum that we could obtain. Okay, now the question is how to detect this DSNB. Well, currently there is one channel which is always used, is the so-called inverse beta decay, where an anti-neutrino, electron anti-neutrino will interact with a proton to produce a positron and a neutron. Well, this leader scheme here with Cherenkov light, this is the example in the water Cherenkov detectors, but that would be the same in liquid scintillator experiments. And the region where we want to look at this DSNB is a relatively small region in energy with typical energies of 10 MeV. And the reason for that is that we're bounded at low energy by spallation background and reactor antineutrinos, and at higher energies by atmospheric neutrinos. The reason why we want to use the IBD is double. First of all, it's obvious that it's the dominant cross-section in the interest region, but also the fact that we have both a positron and a neutron, and the fact that we can detect those two signals in temporal and spatial coincidence makes a powerful tool to reject most of the background. So this is a plot showing you the latest results from different papers. And, well, you can see that, well, depending on the experiments, we are now touching, and even sometimes we are slightly lower than the different theoretical predictions. What is important from an experimental point of view is that you have mostly two technologies, water Cherenkov detectors, which contributes at the higher energy, and liquid scintillator detectors. Now, if you look to those results, which are the flux limit on the anti-nu-E coming from the DSNB, well, you can see that those different detectors, they don't have the same size. And you can see that for Borexino or SNO or even Camlan, we reach the order of 1 kiloton. And what dominates now at higher energy is this Super Kamiokande experiment with this, it's 22.5 kiloton detectors. Though water Cherenkov detectors have, poor performances at very low anti-nu-E energy. Now, you might have seen in this plot those green points, which correspond to the Super Kamiokande phase 6 with gadolinium inside the detector. So I don't want to comment them right now. I will do it in the next few slides in detail. Now, for the near and future, there will be at least 2 new detectors that I will comment. Juno, in the case of liquid scintillator, Hyperkamiokande in the case of water Cherenkov detectors. Well, for Hypercamioconde, it's relatively simple, at least on the principle. You take Supercamioconde, you increase the dimensions of the detector to get a factor roughly 10 in the volume, and you have a 260 kiloton detector. The detector is supposed to start on the 1st April 2027, the beginning of the Japanese fiscal year. And the predictions, you can find them in the letter of intent and technical design report, our expectation of 4 sigma in 10 years to observe the DSNB. One caveat that I should mention is that those plots are assuming 70% neutron tagging efficiency, which may be true if in the end Hyper-K has 40,000 photomultiplier tubes. But right now, at the present time, only half of them are I mean, we have the money to build. Well, of course, we hope to reach 40,000 photomultiplier tubes. And because they are twice more efficient than what we have in Supercamioconde right now, we can assume this 70% neutron tagging efficiency would be more around 40% if we only have half of them. Yeah. Yes? Yes. It's due to statistical fractation. I will show you, like, with the arrow bars, next few slides. If you allow me a comment, which I should probably not say, but I will, should increase the size of the bins so that we don't have statistical fluctuation. And in fact, that's what we have done now with those larger bins in green. Yes. But in this case, we didn't have for SK123 the neutron tagging efficiency, which have reduced a lot the background, but also the signal. Yes, this is the so-called spallation background. If you allow me, can I describe that in a few slides in more detail? Thank you very much. Well, I just wanted to give you a picture of the status of the civil work of the construction of Hyper-K. So this was taken on June 11. So we are on the schedule to start in 2027. Now there is another very interesting experiment which is supposed to be ready right now, although I don't have news like in the last few months. But Juno is supposed to start this year. And Juno, although having a smaller detection volume of 20 kiloton, is still a detector filled with liquid scintillator. And we can do a lot of interesting physics with this detector. And especially with the use of the liquid scintillator, and especially the fact that we can do pulse shape discrimination methods, Juno expect to get a signal over background ratio of 3.5. And that means typically for, well, slightly optimistic prediction, but anyway, you can read the paper if you're interested. They claim they can reach 5 sigma within 10 years. And this is really also interesting. So that means that the future for the next 10 years is covered by Hypercamioconde and Juno, at least in the search for the DSNP. Now I would like to spend a bit more time to comment on the latest Supercamioconde results with gadolinium, which were presented at Neutrino 2024. Well, just Supercamioconde in few words and water Cherenkov in general. Well, I guess most of you know or already know and heard a lot about Super-K, but it's located in Japan, and it's a 50 kiloton water Cherenkov detector, which is subdivided into 2 regions. The inner region, where we look for the signal, and the outer region, which primarily serves as a veto. And in the inner region of the detector, we have roughly 12, photomultiplier tubes of 50 centimeters, 20 inches, and 2,000 of them in the outer region. One thing which is important, especially because I had already a question on the spallation background, is that the overburden is of 2.7 kilometer water equivalent. SK is running since more than 25 years, and I will show you, I hope, that SK can still teach us a lot. So regarding water Cherenkov, if you're not familiar with that, well, just few words about that. When you have an interaction in the detector, typically a neutrino of a given flavor L, which produce the associated charge lepton L. If this lepton travels faster than the speed of light in water, it will emit light in the form of this Cherenkov cone that you see here. And the idea of those water Cherenkov detectors is that you have photomultipliers all around the detector, and you want to detect those rings. And then using special techniques, you can distinguish the pattern, for example, between an electron and a muon. This ring is much more fuzzy than this one, so you can also do PID discrimination. Pages, although true, are in fact, I should not have shown those pictures, because in reality, those events, the typical events that we show, have energies of hundreds of MeV. And in the case of a DSNB signal, a 10 MeV electron would look much more like that, making the finding of the ring much more difficult, technically speaking. Anyway, so SK has started in 1996, as I already said. But what is really important is that it's since SK4, so in September 2008, that the electronic had been upgraded. And with the upgraded electronics, we are able to find a neutron. The capture of the neutron happens hundreds of microseconds after the light emitted by the positron. And with the improved electronic, it was possible to reduce a lot the background by detecting the positron, the prompt signal, and the delay signal coming of the neutron. So neutron tagging, which you will see is a key ingredient of the analysis, is only possible since SK4. So that's still, I mean, quite a lot of data. And also, I will come to that, but since August 2020, the detector has been doped first with 0.01% in gadolinium, and since June 2022 with 0.03% gadolinium in mass. So why is it important, and why is it good to have gadolinium in the detector? Well, everything comes with the detection of this neutron. So without gadolinium, this neutron will be captured on a hydrogen nucleus, and this capture will release a single gamma ray of 2.2 MeV, which is relatively difficult to detect with the superchemical detector. We have roughly 25 to 30% detection efficiency. Now, with gadolinium, the cross-section first is much higher, which means the neutron will be captured in a faster time. And moreover, and this is more important, the signature of the gadolinium, the excitation, will be in the form of several gamma rays with a total energy of 8 MeV, making the signal much easier to detect with the detector. Well, the upgrade process, I don't want to spend too much time on that, but basically the first proof of concept was in 2002. There were dedicated prototype detector built to test the adjunction of gadolinium in water. This is not something you can do just putting some gadolinium powder and expect your detector will be working. You need to encapsulate the gadolinium. And after a major refurbishment of the SK detector since 2020, SK is doped with 0.01 and then 0.03% gadolinium. This gives you typically the fraction of captures of gadolinium as the percentage of the gadolinium mass. So you see that with 0.01% in mass, you already have 50% of the capture which will happen on gadolinium and not on hydrogen. And the reason for that may not be obvious, but it's really because of the cross-section. You can see the cross-section for the thermoneutron cross-section for gadolinium is about 50 kilobars, whereas the one on hydrogen is about 0.3 barns. And because of this huge difference in cross-section, only a small fraction of gadolinium is enough to have a lot of captures on it. So that was the status in August 2020. And currently, we are now with 40 tons of gadolinium sulfate in the detector, which means 75% of the captures happen on gadolinium. So do we have a proof it's working? Yes. So those plots were, in fact, concerned this phase with 50% of the capture on gadolinium. But you can see typically that the energy of released after a neutron capture after spallation of oxygen by a cosmic muon before having gadolinium in the detector gives you this peak in red, so roughly 2.2 MeV gamma ray, of course, with energy resolution of the detector, and that with gadolinium, we now have this shoulder here, which corresponds to those 8 MeV gamma rays. Also, in terms of mean capture time, you can see that there was a, sorry, the beam size are not the same, so, but anyway, the time constant of the exponential for the red points was about 200 microseconds, and it has been reduced to 136 with gadolinium. Okay, so now about the background. So I'm really sorry about this slide. It's rather complicated, but I will try to be as clear as possible because this is really important in the explanation of what we observe right now. So we have at least 4 sources of background. We have atmospheric neutrinos, which have 2 contributions. At low energy, it's the NCQE event, so neutral current quasi-elastic interaction, which dominates. So basically, you have any kind of neutrinos which will interact with an oxygen-60 nucleus, emitting a neutron, and the de-excitation after the interaction might produce one or several gamma rays, which may be identified as the prompt event. This is really dominant at lower energy. At higher energies, it's dominated by charge current interactions and also by pion production. Why are muon and pion a problem? The problem is that if they are produced with not enough energy, they are invisible in the detector. They are below the Cherenkov threshold. But still, they will decay into electron in the end, which will produce this Cherenkov ring associated with a neutron if you had an anti-particle in the initial state. Because anti-nu-E have neutrons, or I should say because nu-E and nu-mu don't have neutron produced in the final state, you can easily reduce nu-E, nu-mu, CC with neutron tagging. However, anti-nu-E, CCQE are completely irreducible, which sets the upper threshold of the analysis. Now, for the lower threshold, we have 2 problems. Reactor neutrinos. Well, reactor neutrinos are anti-nu-E, and the amount of anti-nu-E coming from reactor is much higher than the DSNB. So this sets the analysis lower threshold to something around 8 MeV. But we also have this cosmic ray muon spallation. And this cosmic ray muon spallation is a problem because even with 2.7 water equivalent, we still have 2 hertz of muon in the detector. And those muon will break the oxygen nucleus, and they will produce what we call spallation isotopes. And those spallation isotopes, they will decay, emitting an electron, which mimics the IBD. So you might... It's true, but the problem is that the amount of spallation background events is so high. I'm speaking about 1 million times higher than the DSNB event, that even a very small mistag rate in the neutron identification will create background. So we need to cut those spallation isotopes, plus you have some of them which are beta N emitters. Typically, this is the case of lithium-9. And lithium-9 is really a background for us. So anyway, neutron tagging will help reducing the influence of beta emitters, but still we cannot go very low I mean, we cannot reduce our threshold if we don't take this spallation process into account. And we also have solar neutrinos. Well, solar neutrinos, they do exist, but we have efficient way to remove them because they don't produce neutron in the final state. They are nu E, not anti-nu E. And also we can do some directional cuts using the position of the sun. We know where the sun is at each moment. And therefore, we can remove those events. Now, the situation is this way. Without any reduction, this is the situation we're facing. This is the SK7 Monte Carlo. So this is typically the DSNB signal in the case of a Hoyuchi plus 09 model. And this is the different type of backgrounds. So we will apply data quality cuts, cuts to remove the spallation background, cuts to remove the atmospheric background. And what is really important, we use neutron tagging algorithm. And in fact, in SK, there are two of them. One which is based on a boosted decision tree and one which is based on a neural network. And in the end, applying all those chain of reductions, we end up with this situation here, where you see a window is open for the search of the DSNB. Now, all those cuts are optimized. We perform the systematic evaluation for all those cuts. And then, and this is important to understand the results, there are two independent analysis. One which is model independent. It's a binned analysis. And one is a spectral analysis where we will fit the DSNB on the. And so those two analyses are performed also with two different neutron tagging algorithms that will end up in 4 analyses in the end. So one comment on the paper I promised you. So in 2023, a paper was released with the analysis of the 552 days of SK6 data with 0.01% gadolinium. I must say that this paper was important in the sense that it showed that we were performing well with gadolinium with respect to what we had before. And typically, you can compare the expected limits for SK4 and SK6, those dashed or dot and dashed lines in blue and red. And you can see that with roughly 1.5 year with 0.01% gadolinium, we were a factor 2 or a factor 3 higher in the limits than with 8 years without gadolinium. So it was a nice proof that gadolinium was working. But the caveat of this paper is that it's a cut-based neutron tagging analysis. That means we only have 36% neutron tagging efficiency. So this is, I should say, like a quick and dirty analysis to be published and to prove it was working. But what is really more interesting now is the results which were presented. And well, for the result presented this summer with respect to this published paper, there are many improvements, but I highlighted 3 of them. First of all, we have additional 400 days of data with now 0.03% gadolinium. That is to say 70% of the capture on gadolinium. We in fact have new reduction techniques, and especially one for NCQE events. And this technique is relatively new, but we are able to remove 90% of the NCQE background with this technique. And as I mentioned before, the previous analysis was cut-based, and now we have those 2 machine learning-based neutron tagging method, the boosted decision tree, which was in fact already used in the paper published with SK for the SK4 results, and a new neural network. And we achieve typically in SK7 more than 60% neutron tagging efficiency. Now, here are the preliminary results, which I think, well, not all the plots were shown, but the sum of the 2 were shown during Neutrino 2024. So this is the results of the bin analysis. So the energy spectrum. So this is SK6, and this is SK7. Well, sadly today, not claim anything. I guess you would have known about that before my talk. what we see is that we have few excess of events in SK6, and we don't have any excess so far in SK7. So is it a positive fluctuation here or negative fluctuation here? Well, that's the problem with statistical fluctuation. We don't know. But we also had a hint of a signal in SK4. So when you combine SK4, SK6, and SK7, this is the spectrum we obtain with, well, some excess of event, but it's not. I mean, it's not really. I mean, it's not significant at the present time. Now, well, we don't observe a signal, at least not significantly, but we can still set limits on the DSNB flux, and this is what is shown here, where you have the SK4 results in blue, SK gadolinium, so 6 and 7 in red, and the combination of the 4. And you can see now we are really now touching the different models, and we have also optimized the bin widths to increase our sensitivity to the DSNB. I should note that these results here are for the BDT, but we get very similar limits in the case of the neural network analysis, and that we understand the differences between those two algorithms, and also that among all those phases, we take into account the correlation between the phases. We don't consider all the phases as being independent. And well, now we have the most stringent sensitivity in this 9.3 to 31.3 MeV regions. And well, I will show you, but we are completely statistically dominated, so we can expect well, appreciable sensitivity in the near future. Now, regarding the second analysis, the spectral fitting analysis. So I don't want to go into too much technical detail, but to give you an idea of what we're doing, the first thing is that we're splitting the data into 6 regions. So 3 regions in the Cherenkov angle, low Cherenkov angle sideband region, the signal region, and a high Cherenkov region. In the low region, we expect mostly muons and pions, which are very close to the Cherenkov threshold, so having a very small Cherenkov opening angle. And in this sideband, we expect more NCQ events, where in fact you have multiple gamma rays that you're not able to separate, which form something which looks like a very broad Cherenkov ring. And you have the 2 regions, so here the neutron, the number of tag neutron is exactly equal to 1, and in those regions the number of tag neutron is either 0 or more than 1. And what we are doing is feeding those PDFs, so we have 1 signal, which is the DSNB, and 5 backgrounds, nu ECC, decay electron, NCQE, mu pi, and spallation background, and we fit so those 6 PDFs in those 6 regions on the data. And of course, we have systematics as treated as shape nuisance parameters, and we use frequentist inference for the statistical approach. So now, looking at this plot, here are the data. It's exactly the same data than before. I should note, sorry, should have mentioned that. All those quality cuts are applied the same way on the 2 analyses. So the events we're looking at in the end between the 2 are the same, except here they are separated into the 6 signal regions, whereas before, in the bin analysis, we only used n tag equal 1 region, so this region here, with also a constraint on the Cherenkov angle. Now, if you fit all those data, so this is for SK6, those 550 days, you can see that the contribution from the DSNB, so you need DSNB here and here to explain the excess. So that's what was showed, in fact, at Neutrino 2024 conference, that SK6, if you want to explain the data in the fitting procedures, you need some DSNB signal. Of course, well, I mean, the excess in the SK6 and, well, SK 6 and 7, in fact, is about 1 sigma, and we had, well, about 2 sigma excess in SK1 to 4. So the combined results is this black point that you see here, so a 2.3 sigma excess. So are we close to discovery or not? Well, the problem with statistical fluctuation is that they are statistical by nature. But still, we now have a best fit rate, and I guess at this time more interesting, a 90% confidence limit of 5 events per year, or 2.5 events per centimeter square per year at 90%. Oh, yeah, sorry, I thought. So 6 is this red here, with the best fit somewhere here around 4 per centimeter square per second. And 7 is sadly this purple, oh, sadly, well, results are what they are. This purple line here, where basically we observe no excess. Yes. And SK, just to mention, because that drives our sensitivity, SK4 is the orange curve here with the best fit well, something slightly above 2.5 per centimeter square per second, but also because we had much longer data taking time, it's more significant because we crossed this 2 sigma line. This is in fact an excellent question, and the answer is here. No, I love when we ask me questions which are next slide. So, well, what I can say is that currently we are completely dominated by statistical error. So you can see the best fit. I mean, almost doesn't depend on the model. Of course, we have slightly different best fit, but you can see it's roughly at 1.5 per centimeter square per second. And well, basically, the model-dependent analysis sets currently model-independent limit because of this, well, because the fact we're completely statistically dominated. So far, we cannot say much. Well, we can say that at least this very old Totani plus 96 model has been ruled out, at least at 3 sigma, but not much more so far. So now, well, I think it's time for my conclusion. Well, DSNB flux carry a lot of information, not only on the supernova emission process, but also on the star formation rate, on the cosmic expansion, and also on neutrino properties. Well, we currently have detectors running, and we also have 2 detectors foreseen, so Juno and Hyperkamiokande. That will continue to look for well, this DSNB. But I should say that Super Kamiokande with gadolinium will run at least for the next 3 years with the start of Hyperkamiokande. And depending, of course, on how many events we will detect or not, it might be extended for a few more years. Sadly, I mean, it's a highly political decision. It depends a lot on how many money the Japanese government will have. So this is something I cannot conclude. But at least for the next 3 years, we'll continue to take data with Super Kamiokande. The latest update of the DSNB search were presented at Neutrino 2024 and today, obviously. And well, the conclusion at the present time is no significant DSNB signal, some excess in some means. We are, from the best fit, we're at the 2.3 sigma from the hypothesis. Now, one of the things which is important, and that's what we are doing right now, is if we can lower the threshold in our analysis, we can gain a lot. Because as you have seen, the flux of the DSNB exponentially decreases with energy. So each MeV, each 2 MeV we can gain help us a lot in detecting the event. And this is what we are doing right now, but it requires a consequent work on the spallation probability density function. A lot of things to understand. But well, we hope to continue this work, and we're well, looking forward to the discovery of the DSNB, let's say in the next decade.
I may maybe start asking you how much you think you would be able to lower the threshold. This is, for example, is important for the decay. You know that when you consider decay, you have this peak just
Yes.
below,
Yes.
depending on tau over m. So
it's a bit difficult to answer because we're still in the middle of the process. But let's say, if I go back to here, in this NTAG different from one region, probably not by much. However, in the NTAG region, because we require NTAG equal 1, the only thing which is remaining is the lithium-9. And we probably can do a lot of work on the lithium-9. It has been measured. We can do some simulation. So we have good hopes in this region to lower the threshold. And the dream in this analysis would be to reach, in fact, the threshold that we have here. So around 8, well, 10, 9 MV maybe. Yeah.
And curiosity, why are you applying a frequentist approach and not Bayesian, for example? Is it just because of statistics or why? I mean, I would have expected that you would use a Bayesian approach.
Honest answer is, I think the guy who knows, who's the real expert in the statistics in the DSNB group at SK, is a true frequentist. So that's why he pushes us to that. I personally think that it would be good if we can do both approach. It's always better. And well, if you don't see big disagreement between the two, that gives more credit to your claim or, yeah.
Okay. So other questions? Yeah, Georg.
So these hyperkande sensitivities were without gadolinium, right?
Sorry?
The hyperkande
Yes.
predictions or forecasts were without gadolinium, is that correct?
Yes, they have been done without gadolinium.
And then my follow-up question is then how do we compare super K with gadolinium, with hyper K without gadolinium? Is one of them obviously better or equivalent? I mean, if we had our choice, which one should be running for 10 years?
For now, because we are completely statistically dominated, hyper K for 10 years would be better and super K with gadolinium. Now I should look to the predictions, but because you for sure gain a lot with gadolinium. But having 10 times the larger fiducial volume is still better at the present time. No, I thought your question or complementary question is why not putting gadolinium into hyper K? And this is something I will push with my colleagues to the hyper K community a lot in the next few years. The problem is you need 10 times more gadolinium that we have right now in super K because of the 10 times bigger volume, which, if I remember correctly, is the equivalent of 2 years of worldwide gadolinium production. And we reject some of the production because it's too radioactive. So might be a bit difficult to reach the same concentration. But I would love to have gadolinium in hyper K.
Other questions or comments? Yeah, Michiro. Yeah, sure.
Yeah, actually, I'm curious about how you would solve the degeneracy between among the integral, which gives you the DSNB flux, namely that you have RSM and also the neutrino flux from one supernova event, and also you, as you mentioned, you have it's a integral cosmic time, so that it also involved with the cosmic expansion. So how after you find the signal, how do you degenerate those information?
That's an excellent question, where I must admit I don't have the answer. I'm not sure how we will be able to discriminate between the degeneracies without having a really good sensitivities between the different energy beams. Well, no, the NO tensors, I don't know at the present time. I don't know if it will be possible or not. But first, let's discover the DSNB, and then, yeah, of course, that would be very interesting to see. There are some effects still in the spectrum which have higher importance. Typically, the fraction of black hole forming supernova and the temperature of the core plays a huge role in the shape of the spectrum. It's like 20 to 30% effect. So this one we could discriminate from other maybe subdominant effects, but between the two, it's for me impossible at the present time to answer.
Andre, do you know? Okay. If there are no more questions, let us thank Thomas for this very interesting talk.